Today, we are diving into one of the most profound and groundbreaking concepts in physics, the theory of relativity. This theory, which revolutionized our understanding of space, time, and gravity, is a cornerstone of modern physics. The theory of relativity is often divided into two parts: special relativity and general relativity. Special relativity, formulated in 1905, challenged the traditional views of space and time, while general relativity, published in 1915, extended these ideas to include gravity, offering a new way to look at how massive objects influence the fabric of space-time. Special relativity introduced the famous equation, E equals mc squared, which showed that energy and mass are interchangeable. This equation helped to unlock the secrets of nuclear energy and led to the development of modern technologies. It also suggested that the laws of physics are the same for all observers, no matter how fast they are moving, as long as they aren't accelerating. This insight led to the realization that time and space are not fixed but can change depending on how fast we are moving or how strong the gravitational field is. General relativity, on the other hand, took the ideas of special relativity further by explaining gravity not as a force, but as a curvature of space-time caused by the presence of mass. This was a revolutionary shift from the Newtonian view that had been dominant for centuries. Instead of objects being pulled by gravity, general relativity proposes that mass warps the fabric of space-time, and objects simply follow the curves in that fabric. These theories have been confirmed through various experiments and observations, such as the bending of light by gravity, the movement of planets, and even time dilation experiments with atomic clocks. These findings have opened the door to a deeper understanding of the universe and have paved the way for advancements in technology, astronomy, and cosmology. Relativity has had a profound impact, not just on physics, but on our everyday lives as well. Global Positioning System, GPS, technology, for instance, relies on relativity to provide accurate positioning data. Without factoring in the time differences due to both special and general relativity, our GPS systems would be off by miles. In conclusion, the theory of relativity represents a monumental shift in how we view the universe. It has reshaped our understanding of the nature of time, space, and gravity, and continues to inspire further discoveries in the field of physics. The work done in this area has not only advanced scientific knowledge, but also led to practical applications that affect our daily lives. The theory of relativity is one of the most significant achievements in the history of modern physics, and it consists of two groundbreaking theories: special relativity, introduced in 1905, and general relativity, formulated in 1915. While they are related, each theory addresses different aspects of space, time, and gravity. Special relativity, proposed in Albert Einstein's 1905 paper, challenged the conventional understanding of time and space. Prior to this theory, physics was largely based on Newtonian principles, where space and time were considered absolute, fixed entities that were unaffected by motion or other external factors. Special relativity, however, introduced the revolutionary idea that time and space are relative, meaning they depend on the observer's state of motion. One of the key insights of special relativity was the recognition that the speed of light in a vacuum is constant for all observers, regardless of their motion relative to the source of light. This contradicted the ideas of classical physics, which suggested that light's speed could vary depending on the observer's movement. This concept had profound implications, not just for how we understand motion, but also for the nature of time itself. Special relativity also showed that space and time are not separate entities, but are interconnected as a single, four-dimensional continuum known as space-time. The relationship between space and time became dynamic, depending on how fast an object is moving relative to the observer. This shift in understanding was so radical that it required a complete overhaul of concepts like simultaneity, whether two events happening at the same time for one observer could be considered simultaneous for another observer in motion. General relativity, a decade later in 1915, expanded on the ideas of special relativity, addressing the role of gravity. While special relativity dealt primarily with objects moving at constant speeds and without gravitational influence, general relativity incorporated the effects of acceleration and gravity, offering a new way to understand how massive objects, such as planets and stars, interact with the fabric of space-time. In summary, the theory of relativity is a monumental work divided into two parts, with special relativity focusing on the nature of space, time, and motion in the absence of gravity, and general relativity expanding that understanding to include the effects of gravity and acceleration. Together, these theories transformed our fundamental understanding of the universe and laid the groundwork for countless scientific advancements in the years that followed. One of the central principles of special relativity is the idea that the laws of physics are invariant, meaning they are the same for all observers who are moving at constant speeds relative to each other. This is known as the principle of relativity. Before Einstein's theory, physicists believed that the laws of physics could differ depending on the observer's state of motion. For instance, it was assumed that experiments performed in a moving train, for example, would produce different results compared to the same experiments performed in a stationary laboratory. This was partly based on the understanding that there was a universal ether through which light propagated, and that objects in motion relative to this ether would experience different effects. However, special relativity fundamentally challenged this assumption by showing that the laws of physics do not depend on the particular state of motion of an observer. This means that whether an observer is at rest or moving at a constant velocity, in a straight line, the same physical laws, such as the laws of mechanics or electromagnetism, hold true, provided the motion is uniform, i.e., no acceleration. This was a revolutionary shift from previous classical physics, where the frame of reference was often assumed to play a role in determining the physical outcomes of experiments. This principle also applies to the behavior of light. According to classical theories, the speed of light would depend on the motion of the observer relative to the source of light. For example, if a person were moving towards a light source, they would expect to measure the light traveling towards them at a higher speed. But special relativity demonstrated that the speed of light is always constant for all observers, regardless of their motion relative to the light source. This fact forms the cornerstone of the theory and led to many other surprising conclusions. By establishing that the laws of physics are the same for all observers moving at constant velocity, special relativity set the stage for a major shift in our understanding of motion and time. It highlighted the need for a new way of describing how objects behave in different reference frames and necessitated a rethinking of concepts like time, distance, and simultaneity. Furthermore, this principle has had lasting effects not only on theoretical physics, but also on technology and our daily lives. It forms the basis for much of modern physics, including the theories that underpin particle accelerators, atomic clocks, and even the Global Positioning System, GPS. This idea also laid the groundwork for understanding that no matter how fast someone is moving, they would still measure the speed of light to be the same. This principle is sometimes difficult to grasp intuitively because it defies our everyday experiences. After all, if you are moving toward a car that is speeding away from you, you would measure the speed of the car as different than if you were standing still. But light, according to Einstein's theory, behaves in a radically different way. In summary, the introduction of the principle of relativity in special relativity was not just a new idea about motion, it was a deep reimagining of the very fabric of the laws of physics. It unified the understanding of physics for all observers moving at constant velocities, established the speed of light as a universal constant, and laid the foundation for future breakthroughs in physics, technology, and our understanding of the universe. One of the most famous and profound outcomes of special relativity is the equation E equals mc squared, which reveals that mass and energy are not separate, but are actually interchangeable. This equation has become synonymous with Einstein's theory and is one of the most well-known scientific formulas in the world. The E represents energy, the m represents mass, and the c represents the speed of light in a vacuum, approximately 299,792,458 meters per second. The equation suggests that a small amount of mass can be converted into a huge amount of energy and vice versa. The idea that mass and energy are related was a revolutionary concept. Prior to this, mass and energy were considered distinct and unrelated properties. Mass was thought of as the substance that makes up objects, while energy was the ability to do work. For instance, an object might have potential energy, such as a rock held at a height, or kinetic energy, such as a moving car. but these forms of energy were thought to be separate from the object's mass. Einstein's insight, however, showed that mass could be viewed as a form of energy, and energy could be thought of as a form of mass. The implication of this equation is profound. It means that mass itself has an intrinsic energy that is locked inside it. This energy can be released through processes that convert mass into energy. A prime example of this is nuclear reactions. In nuclear fission, when the nucleus of an atom splits, a small amount of the mass is converted into an enormous amount of energy, which is the principle behind nuclear power plants and atomic bombs. Similarly, in nuclear fusion, the process that powers the sun, hydrogen atoms fuse to form helium, and the mass difference between the two is converted into energy, which radiates as light and heat. This concept also helps explain why the speed of light plays such a critical role in the equation. The speed of light, being an extremely large number, suggests that even a small amount of mass contains an enormous amount of energy. This is why the conversion of mass to energy, though it may seem like a small change, can result in such large amounts of energy. For example, just a tiny amount of matter, if converted into energy, could release a tremendous amount of power. This relationship between mass and energy is what makes nuclear reactions so powerful. Moreover, E equals mc squared also helps to explain why objects with mass cannot travel at the speed of light. As an object with mass approaches the speed of light, its energy increases dramatically. The closer it gets to the speed of light, the more energy is required to continue accelerating it, and at the speed of light, an infinite amount of energy would be needed. This makes it impossible for any object with mass to reach or exceed the speed of light. In addition to its applications in nuclear energy, the equation E equals mc squared is foundational to many other areas of physics and technology. For example, it plays a key role in particle physics, where high-energy particle accelerators smash particles together to create new forms of matter. These experiments and many others in the field of physics are directly influenced by our understanding of the mass-energy equivalence. Furthermore, the idea of mass-energy equivalence is important in cosmology and astrophysics. In the case of stars, the balance between the energy produced by nuclear fusion and the mass of the star determines its size, temperature, and life cycle. E equals mc squared helps explain how stars shine and how they evolve over time. It also plays a role in understanding phenomena like black holes and the Big Bang. In conclusion, E equals mc squared is more than just an equation. It is a fundamental principle of the universe that shows the deep connection between mass and energy. It has profound implications for both theoretical and applied physics, helping us to understand everything from the smallest particles and accelerators to the immense power of stars. Before the advent of special relativity, the prevailing belief in classical physics was that time and space were absolute. Time was considered to flow the same way for everyone, everywhere, and space was a fixed, unchanging backdrop within which events occurred. This view was heavily influenced by the ideas of Isaac Newton, who believed that time and space existed independently of the events that happened within them. For example, if you were to measure the time it takes for an event to occur, it would be the same regardless of where or how fast you were moving. This perspective remained unchallenged for centuries and formed the foundation of much of classical mechanics. However, Einstein's theory of special relativity fundamentally altered this understanding. One of the key revelations of the theory was that both time and space are relative, meaning they can change depending on the observer's state of motion or the strength of gravitational fields they are in. This was a complete departure from the Newtonian conception of fixed time and space, and it required a new framework for understanding how the universe operates at high speeds and in different gravitational environments. The most famous example of this relativity of time is the concept of time dilation. According to special relativity, as an object moves closer to the speed of light, time begins to slow down relative to an observer who is at rest. This effect, known as time dilation, occurs because time is not an absolute quantity. For someone traveling at near-light speeds, time would appear to pass more slowly compared to someone who is stationary. This means that a person moving at high velocity would age more slowly than someone who remains at rest. To illustrate, imagine two twins. One stays on Earth while the other travels into space at a velocity close to the speed of light. When the traveling twin returns, they will have aged less than the twin who remained on Earth. This thought experiment, known as the twin paradox, may seem strange, but it has been confirmed through experiments involving fast-moving particles, which decay slower when moving at high velocities, as well as with atomic clocks flown in aircraft, which tick at a slower rate compared to clocks on the ground. Space itself also undergoes transformations at high speeds. According to special relativity, as an object moves faster, its length in the direction of motion appears to contract. This phenomenon, known as length contraction, means that an object moving at a significant fraction of the speed of light will appear shorter to an observer who is not moving with the object. While this effect is incredibly small at everyday speeds, it becomes more pronounced as you approach the speed of light. The relationship between time and space is not independent, but interconnected in a four-dimensional continuum known as spacetime. This means that changes in one dimension, either time or space, will affect the other. For example, the faster an object moves through space, the slower it moves through time. This interdependence between space and time is at the heart of special relativity and highlights that neither time nor space can be thought of as fixed, independent quantities. Moreover, these relativistic effects are not limited to the high speeds that are difficult to achieve with everyday objects. Time dilation, for example, has practical applications in modern technology. A prominent example is the Global Positioning System, GPS. GPS satellites orbit Earth at very high speeds and experience weaker gravitational fields compared to clocks on the surface. As a result, their onboard atomic clocks tick slightly faster due to the effects of both special and general relativity. Without accounting for these relativistic time differences, the positioning data from GPS satellites would be inaccurate by several kilometers. The implications of special relativity also extend to understanding the nature of the universe itself. It suggests that there is no universal now that all observers share. What one observer perceives as happening at the same time, another observer, moving at a different speed or in a different location, may perceive as happening at different times. This challenges our everyday sense of simultaneous events and leads to a more complex and nuanced view of reality. Furthermore, the effects of special relativity aren't limited to speed alone. They are intertwined with the effects of gravity, as will be further explored in general relativity. While special relativity focuses on uniform motion, no acceleration, general relativity shows that time and space are also influenced by gravitational forces. In a strong gravitational field, time slows down, an effect known as gravitational time dilation, which was confirmed when clocks at different altitudes on Earth ticked at slightly different rates. This shows that time is not just relative to the observer's motion, but also to the gravitational environment in which the observer is located. In summary, special relativity shattered the classical view of time and space as absolute, showing that both are flexible and can change based on the observer's speed or position. These changes, such as time dilation and length contraction, have been proven through experiments and have far-reaching implications for everything from space travel to the design of technology, like GPS. The realization that time and space are relative, interconnected, and dependent on motion has fundamentally altered our understanding of the universe and continues to be a key part of both theoretical and applied physics. One of the most profound and revolutionary ideas introduced by general relativity is the concept that gravity is not a force transmitted through space, as was proposed by Sir Isaac Newton. Instead, gravity is a manifestation of the curvature or warping of space-time itself, caused by the presence of mass and energy. This idea fundamentally changed our understanding of how objects move through the universe and how gravitational interactions occur. In Newtonian physics, gravity was described as a force of attraction between two masses, such as the Earth and an apple. This force acted instantaneously, meaning that if you moved an object, the change in gravitational influence would be felt immediately across the distance between them, no matter how far apart they were. However, this view had limitations and could not explain certain phenomena, such as the precise motion of planets in orbit around the Sun or the bending of light by gravity, which had been observed during solar eclipses. General relativity offered a new perspective by proposing that gravity does not act as an invisible force. Instead, it results from the curvature of the four-dimensional fabric of spacetime, which is caused by the mass and energy of objects. Spacetime, in this theory, is not a static, rigid backdrop against which events occur. Rather, it is a dynamic, flexible structure that can bend, stretch, and curve in response to the presence of matter and energy. To understand this concept, imagine spacetime as a stretched rubber sheet. When you place a heavy object, like a bowling ball, on the sheet, it causes the sheet to warp or dip around the ball. If you then roll a smaller object, such as a marble, across the sheet, the marble will follow a curved path as it moves toward the bowling ball. This analogy helps illustrate how massive objects, like stars and planets, curve the fabric of spacetime, causing other objects to move along curved paths, which we perceive as the force of gravity. However, unlike the rubber sheet, spacetime is a four-dimensional continuum, and the curvature affects not just space, but also time. This idea that mass curves spacetime is the core of general relativity. The greater the mass of an object, the more it warps the fabric of spacetime, and the stronger the gravitational effect it has on nearby objects. For example, the Sun, with its massive gravitational pull, causes a significant curvature in the surrounding spacetime, which is why the Earth and other planets follow elliptical orbits around it. Rather than being pulled toward the Sun by a force, the planets are following curved paths in the warped spacetime created by the Sun's mass. One of the most famous predictions of general relativity is the bending of light around massive objects, a phenomenon known as gravitational lensing. According to Einstein's theory, light, despite having no mass, should also follow the curvature of spacetime. This was confirmed during a 1919 solar eclipse when astronomers observed that the light from distant stars was bent as it passed near the Sun, a phenomenon that could not be explained by Newtonian gravity. This bending of light occurs because the massive Sun curves spacetime, causing the light to follow a curved trajectory, and is a powerful demonstration of the validity of general relativity. Another important aspect of general relativity is that it predicts the existence of black holes, which are regions of spacetime where gravity is so strong that not even light can escape. These black holes are formed when a massive star collapses under its own gravity, creating a singularity, a point where space-time curves infinitely. The study of black holes and their associated phenomena, such as event horizons and gravitational waves, has become an exciting field of research, confirming and expanding upon the predictions made by general relativity. Moreover, general relativity also provided a new understanding of the behavior of time in strong gravitational fields. Time itself moves slower near a massive object due to the warping of space-time. This phenomenon, known as gravitational time dilation, has been confirmed by experiments involving highly accurate atomic clocks. Clocks placed at higher altitudes, where the gravitational pull is weaker, tick slightly faster than those placed at lower altitudes, where the pull of gravity is stronger. This effect, though tiny, is crucial for the accuracy of satellite-based technologies, such as GPS, which must account for the different rates at which time passes at different altitudes and velocities. The theory of general relativity also reshaped our understanding of the universe on a large scale. It predicted the expansion of the universe, the bending of light by galaxies, and the existence of gravitational waves, ripples in space-time caused by the acceleration of massive objects, such as two black holes merging. In 2015, the detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, confirmed one of the key predictions of general relativity and opened a new era of astrophysical observation. In conclusion, general relativity redefined our understanding of gravity. It replaced the idea of gravity as an invisible force with the notion that massive objects warp the very fabric of spacetime, influencing the motion of everything within their gravitational reach. The curvature of spacetime is not just an abstract concept, but a real and observable phenomenon that affects everything from the orbits of planets to the bending of light and the behavior of time. Through its profound insights, general relativity has not only expanded our understanding of the cosmos, but also provided the foundation for a wide range of scientific advancements in astrophysics and cosmology. General relativity, since its formulation in 1915, has undergone numerous tests and experiments, all of which have provided strong evidence in support of its predictions. Unlike many other scientific theories, which may be difficult or impractical to test directly, the predictions made by general relativity have been subject to rigorous experimental and observational verification. These tests span across a wide variety of phenomena, from the bending of light to the movement of planets and the behavior of black holes, and they have continuously confirmed the theory's accuracy and robustness. One of the first major confirmations of general relativity came in 1919 when a team of astronomers, led by Arthur Eddington, observed a total solar eclipse. During the eclipse, they measured the position of stars that were visible near the sun. According to general relativity, the intense gravitational field of the sun should bend the light coming from these stars, causing their apparent positions to shift slightly. Newtonian physics, which viewed gravity as a force acting instantaneously through space, did not predict this bending of light. However, general relativity predicted that light would follow the curvature of spacetime, bending as it passed near the sun. Eddington's observations during the eclipse confirmed this prediction, providing one of the first major experimental validations of Einstein's theory. In the decades that followed, further experiments and observations continued to support general relativity. One such confirmation came from the precise tracking of the orbits of planets, particularly Mercury. While Newton's laws of gravity worked well for most planets, they could not fully account for the orbit of Mercury, which deviated slightly from what was expected. General relativity, however, explained this anomaly by showing that the curvature of space-time near the Sun caused a slight precession, a slow, cyclic shift, of Mercury's orbit. This phenomenon, known as the perihelion precession of Mercury, was another piece of solid evidence supporting the theory. In the 1960s, the development of radio telescopes allowed astronomers to test general relativity even more rigorously. They observed the motion of pulsars, extremely dense, rapidly rotating neutron stars that emit regular pulses of radiation. The behavior of these pulsars, particularly in binary systems where two stars orbit each other, provided further evidence for general relativity. The precise timing of the pulses from these pulsars confirmed that gravitational waves, ripples in space-time predicted by Einstein's equations, were indeed being generated by the motion of massive objects. A groundbreaking test of general relativity came in the form of the detection of gravitational waves themselves. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from the collision of two black holes. This discovery confirmed another key prediction of general relativity, that massive, accelerating objects could create ripples in space-time that propagate outward at the speed of light. The detection of these waves not only validated Einstein's theory, but also opened a new field of astrophysical research, allowing scientists to observe the universe in a completely new way. Perhaps one of the most compelling confirmations of general relativity has come from observations of black holes. These mysterious objects, whose gravity is so strong that not even light can escape, were theoretical predictions of general relativity, and they have since been observed in a variety of astronomical systems. One of the most remarkable observations came in 2019 when the Event Horizon Telescope, EHT, collaboration released the first ever image of a black hole's event horizon, its shadow, located at the center of the galaxy M87. This image, which showed the dark region surrounded by a glowing ring of light, matched the theoretical predictions made by general relativity for the shape and structure of a black hole's event horizon, providing direct visual evidence for the existence of black holes. Additionally, the behavior of matter around black holes has provided further evidence for general relativity. In particular, the way light and other forms of radiation are bent and distorted as they pass near black holes, known as gravitational lensing, aligns precisely with the predictions of general relativity. This effect has been observed in multiple instances, such as in the case of quasars, extremely energetic and distant galaxies with supermassive black holes at their centers, which are often distorted by the gravitational fields of intervening objects, confirming the theory's accuracy. The fact that general relativity has been consistently confirmed through such a wide variety of observations and experiments, from bending light around the sun to the detection of gravitational waves and the study of black holes, has solidified its position as one of the cornerstones of modern physics. In fact, general relativity has not only passed all tests with flying colors, but has also predicted new phenomena that were later confirmed through observation. This predictive power is a key hallmark of a successful scientific theory, and it highlights the deep insights that general relativity provides into the nature of space, time, and gravity. Furthermore, the theory has practical implications that go beyond theoretical physics. For example, the very technology that many people use every day, GPS, requires accounting for the effects of general relativity. GPS satellites orbiting Earth are subject to both time dilation effects due to their high speeds and gravitational time dilation due to their weaker gravitational field relative to the Earth's surface. If the time adjustments predicted by general relativity were not factored in, GPS systems would be inaccurate by several kilometers within just a few minutes. In conclusion, general relativity has not only stood the test of time, but has been confirmed through numerous experiments and observations over the past century. From the bending of light around massive objects to the detection of gravitational waves and the imaging of black holes, the theory has proven to be an extraordinarily accurate description of how gravity works and how space-time behaves. As our observational tools continue to improve, it is likely that general relativity will provide even more insights into the fundamental workings of the universe, further cementing its status as one of the greatest scientific achievements in history. The impact of Einstein's theory of relativity, both special and general, extends far beyond theoretical physics and has profoundly influenced technology, science, and even our everyday lives. While relativity may have initially been viewed as a purely academic pursuit, its practical applications have become integrated into various fields, from the most advanced technologies to fundamental areas of scientific research. The principles of relativity are not only essential for understanding the structure of the universe, but also play an instrumental role in shaping modern technological systems and guiding cutting-edge scientific breakthroughs. One of the most well-known and essential applications of relativity is in the field of global positioning systems, GPS. GPS satellites orbiting Earth are an example of how relativity directly impacts technology in a very practical way. GPS satellites are moving at high velocities, which means that time for the satellites, according to special relativity, passes slightly more slowly than on Earth. Additionally, because the satellites are in a weaker gravitational field than objects on Earth, general relativity predicts that time on the satellites moves faster than on the ground. Together, these effects cause the clocks on the GPS satellites to drift out of sync with clocks on Earth if not corrected. Without factoring in the time dilation effects predicted by relativity, GPS systems would quickly become inaccurate, leading to errors in positioning that could grow to several kilometers per day. Therefore, engineers must adjust the GPS satellite clocks based on relativistic calculations to ensure that the system provides precise location data. In telecommunications, the principles of relativity are also relevant in the context of satellite communication. As satellites move at high speeds in orbit, their clocks experience time dilation, similar to what is seen in GPS systems. Communication between Earth stations and satellites must account for these relativistic time differences to ensure that data transmission is synchronized correctly. Additionally, the concept of relativistic effects plays a role in the design of particle accelerators, which are used to study the fundamental particles of nature. As particles in these accelerators approach speeds close to the speed of light, relativistic effects such as time dilation and mass increase must be carefully considered to accurately predict and measure their behavior. Beyond practical technologies, relativity has also had a profound influence on the development of quantum mechanics and modern physics. In the early 20th century, quantum mechanics emerged as a new framework for understanding the behavior of particles at extremely small scales. However, the unification of relativity and quantum mechanics has posed a significant challenge for physicists. General relativity describes the force of gravity in terms of the curvature of spacetime, while quantum mechanics governs the interactions of particles on the smallest scales, and these two theories are not easily reconciled. Nonetheless, attempts to merge the two have driven the development of theories such as quantum field theory and string theory. Quantum field theory seeks to combine special relativity with quantum mechanics by describing fields of energy that permeate space and interact with particles. String theory, a theoretical framework attempting to unify all of the fundamental forces of nature, including gravity, takes into account both quantum mechanics and general relativity, suggesting that the universe is composed of tiny vibrating strings rather than point particles. In cosmology, Einstein's theory of relativity has provided the foundation for modern models of the universe. General relativity has been essential for understanding the large-scale structure of the universe, including the behavior of galaxies, the formation of stars, and the evolution of the cosmos. The concept of space-time curvature has led to the understanding of phenomena such as black holes, the Big Bang, and the expansion of the universe. In particular, the discovery that the universe is expanding based on observations of distant galaxies moving away from us is a direct consequence of the equations of general relativity. Moreover, the theory has helped guide the study of dark energy and dark matter, two mysterious components that are believed to make up most of the universe's mass energy content, but are not directly observable. General relativity has provided a theoretical framework for understanding how these phenomena influence the expansion of the universe and its large-scale dynamics. Furthermore, relativity has influenced the study of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. The first detection of gravitational waves by LIGO in 2015 was a historic moment in physics, confirming one of Einstein's long-predicted phenomena. The ability to detect these waves opens up a new window into understanding some of the most extreme environments in the universe, such as black hole mergers and neutron-star collisions. Gravitational wave astronomy has already begun to revolutionize our understanding of the cosmos, allowing scientists to study cosmic events that are invisible to traditional telescopes. Relativity also plays a crucial role in the ongoing research in high-energy physics. Particle accelerators, such as the Large Hadron Collider, LHC, rely on relativistic principles to accelerate particles to near-light speeds. The collisions of these particles provide insights into the fundamental structure of matter, and the need to account for relativistic effects in these experiments ensures that our understanding of the particle's behavior is accurate. The discovery of the Higgs boson in 2012, a key particle predicted by the Standard Model of Particle Physics, was made possible by experiments conducted at the LHC, and those experiments were designed with relativity in mind. Additionally, relativity has influenced fields like astrophysics and space exploration. Understanding the effects of relativistic time dilation, space-time curvature, and gravitational waves is crucial for making accurate predictions about the behavior of celestial objects and understanding the dynamics of the cosmos. Space agencies, such as NASA, rely on the principles of relativity when planning missions to distant planets and stars. Calculations for spacecraft trajectories, especially for missions traveling at high speeds, incorporate relativistic effects to ensure that spacecraft reach their intended destinations. In summary, Einstein's theory of relativity has proven to be more than just a theoretical framework for understanding the nature of gravity and spacetime. It has become an indispensable tool in modern technology and scientific research. From its influence on the development of GPS and telecommunication systems to its guiding role in quantum mechanics, cosmology, and astrophysics, relativity has transformed how we view the universe and how we design and utilize technology. Its continued impact on fields as diverse as particle physics, space exploration, and gravitational wave astronomy shows that Einstein's ideas are not only foundational to our understanding of the universe, but are also vital to the advancement of modern science and technology. The theory of relativity, both special and general, fundamentally altered how we perceive time, space, and the very nature of the universe itself. Before Einstein's groundbreaking work, our understanding of time and space was largely influenced by the ideas of classical physics, particularly those developed by Sir Isaac Newton. In Newtonian mechanics, time and space were viewed as absolute and independent entities. Time ticked at a constant rate for all observers, and space was a three-dimensional, rigid backdrop against which objects and events occurred. However, relativity shattered these notions and introduced a completely new way of thinking about the fabric of reality itself. Special relativity, introduced in 1905, revolutionized our understanding of space and time by showing that they are not separate and fixed entities. Instead, they are interconnected and relative, dependent on the observer's frame of reference. One of the most profound revelations of special relativity is the idea that time and space are not absolute, as had been traditionally believed, but are flexible and can change depending on the motion of observers. This concept is encapsulated in the famous equation equals
2
E equals mc,
2
which states that energy and mass are interchangeable and is one of the cornerstones of modern physics. But perhaps more dramatically, special relativity shows that time and space can stretch and bend in response to motion and velocity. The idea that time is relative is one of the most striking consequences of special relativity. Prior to Einstein's theory, time was thought to flow the same for everyone, everywhere. However, special relativity introduced the idea of time dilation, where time slows down for an object moving at a significant fraction of the speed of light relative to an observer at rest. This was a mind-boggling concept. An object in motion, especially at speeds approaching the speed of light, experiences time differently than an observer at rest. The faster an object moves, the more its time is stretched, meaning that a clock traveling with that object would tick more slowly compared to a clock at rest. This effect has been experimentally verified in numerous ways, including using atomic clocks placed on airplanes or satellites, which have shown that clocks on moving objects indeed run slower compared to those on Earth. In essence, time is not a constant, universal flow, but something that can change depending on the observer's speed relative to what they are observing. The concept of length contraction is another consequence of special relativity. Just as time dilates, lengths, or distances between objects, contract in the direction of motion for an object moving at high velocities. For example, a moving spaceship, as observed from a stationary observer, would appear shorter along the direction of travel. This contraction of space is not noticeable at everyday speeds, but becomes significant as the object approaches the speed of light. The consequences of length contraction and time dilation are not just theoretical, they have real-world implications, particularly in areas like particle physics, where particles are moving close to the speed of light. In particle accelerators, where subatomic particles are accelerated to nearly the speed of light, both time dilation and length contraction are essential concepts to understand the behavior of particles. In addition to special relativity, Einstein's theory of general relativity introduced a radically new way of thinking about the force of gravity and its relationship with space and time. Unlike Newtonian gravity, which treated gravity as a force acting at a distance between two masses, general relativity proposed that gravity is a result of the curvature of space-time caused by the presence of mass and energy. In this framework, space and time are not flat and unchanging, but are curved and warped by massive objects like planets, stars, and black holes. This curvature of space-time means that objects in the vicinity of massive bodies do not move in straight lines, but instead follow curved paths, a phenomenon that we perceive as the force of gravity. The impact of general relativity on our understanding of space and time is profound. The presence of mass and energy alters the structure of space-time, causing it to curve and bend. This warping of space-time affects the paths of objects, including light. Light, despite having no mass, is influenced by gravity because it follows the curvature of space-time. This is why we observe phenomena such as gravitational lensing, where light from distant stars or galaxies is bent around massive objects, creating distorted images. This bending of light is a direct consequence of the curvature of space-time, and it demonstrates that space and time are intimately connected in a way that was previously unimaginable. General relativity also introduced the idea that time itself can be warped by gravity. In regions of strong gravitational fields, such as near a massive planet or a black hole, time flows more slowly compared to regions with weaker gravitational fields. This effect, known as gravitational time dilation, has been confirmed by experiments involving atomic clocks at different altitudes. Time runs more slowly for clocks placed closer to a massive object, where the gravitational pull is stronger, compared to clocks further away. This effect has practical applications, such as in the adjustment of clocks on GPS satellites, which orbit in a weaker gravitational field than objects on Earth, where time would pass more slowly. The need to account for these differences in the passage of time is crucial for ensuring the accuracy of GPS systems. One of the most striking and mind-expanding ideas to emerge from general relativity is the concept of black holes. Black holes are regions of space-time where gravity is so intense that not even light can escape. These enigmatic objects form when massive stars collapse under their own gravity, causing space-time to curve to an extreme degree. The event horizon of a black hole marks the boundary beyond which nothing, no matter or light, can escape, and beyond this point, the curvature of space-time becomes infinite, leading to what is known as a singularity. Black holes challenge our very notions of space and time, as they represent regions where the normal laws of physics break down. The study of black holes has revolutionized our understanding of the nature of the universe, showing that space-time can be distorted in such extreme ways that it raises profound questions about the structure of reality itself. Relativity also reshaped our understanding of the universe on a cosmological scale. General relativity provided the framework for understanding the Big Bang, the expansion of the universe, and the structure of space-time itself. The theory predicts that the universe began in a singularity, a point of infinite density, and has been expanding ever since. This expansion continues to accelerate, and it has led to the discovery of dark energy, an unknown form of energy that seems to be driving the accelerated expansion of the universe. The theory also predicts the existence of cosmic phenomena such as gravitational waves, which were first directly detected in 2015, further confirming the notion that space-time is not a static, unchanging entity, but a dynamic, evolving fabric that is influenced by mass, energy, and the forces of gravity. Einstein's theory of relativity has not only transformed the field of physics, but has also raised fundamental philosophical questions that continue to influence how we think about reality, existence, and the nature of the universe. By challenging long-standing ideas about time, space, and causality, relativity has led to a deeper examination of the concepts that govern not just the physical world, but also our understanding of the very nature of the universe. These questions have sparked debates among physicists, philosophers, and thinkers from various disciplines, revealing the profound and sometimes unsettling implications of a theory. One of the most significant philosophical questions that relativity brings to the forefront is the nature of time itself. Before Einstein's work, time was viewed as a fixed and absolute entity, flowing evenly for all observers, regardless of their motion or position in space. In this traditional view, time was something universal that everyone experienced in the same way. However, Einstein's theory of relativity shattered this perception by showing that time is relative. It depends on the observer's speed and gravitational field. This raises the intriguing philosophical question: what is the true nature of time? If time can bend and stretch depending on where you are and how fast you're moving, can we still say it exists in a uniform, absolute sense? This idea forces us to confront the possibility that time is not an objective, independent feature of the universe, but something that is fluid and subjective. The notion of space also undergoes a dramatic shift in relativity. In classical physics, space was treated as a static, unchanging stage where objects moved, independent of the objects themselves. It was a container for events that unfolded within it. However, Einstein's general theory of relativity proposed that space is not just a backdrop, it is an active participant in the universe, capable of being warped and curved by the presence of mass and energy. This warping of space leads to the idea of space-time, a four-dimensional continuum in which space and time are intertwined, not separate entities. This understanding challenges the traditional concept of space as something unchanging and absolute. In the relativistic framework, space is not a passive stage for events, but an elastic, dynamic medium that can be shaped by the objects it contains. This raises a deeper question about the true nature of reality. If space itself can curve and change, what is the underlying substance or essence of the universe? One of the most profound and paradoxical aspects of relativity is its treatment of simultaneity. In classical physics, it was believed that two events occurring at the same time for one observer would also occur at the same time for any other observer, no matter where they were or how fast they were moving. However, special relativity shows that simultaneity is not absolute. Different observers, depending on their relative motion, will perceive events as happening at different times. This concept, known as the relativity of simultaneity, challenges our conventional notions of the objective nature of time. It forces us to reconsider what it means for two events to occur at the same time. Is simultaneity an inherent property of the universe, or is it something that is relative to the observer? This question has profound implications for our understanding of cause and effect, as the ordering of events can vary depending on the observer's motion, making the concept of before and after more fluid than we previously assumed. Relativity has also prompted new discussions about the concept of causality. In classical physics, causality is a straightforward concept. Events occur in a linear cause and effect sequence. However, the theory of relativity introduces the idea that causality may be more complicated than previously thought. The relativity of simultaneity, for example, can lead to situations where two events are observed to occur in a different order depending on the observer's reference frame. This raises questions about whether causality is an absolute concept or if it too is relative. If the order of events can change depending on the observer's motion, does this mean that causality is not as rigid as we once believed? The nature of cause and effect, once thought to be fundamental, now seems to depend on the perspective from which the events are observed. One of the most mind-bending implications of relativity is the concept of time travel, which has been a topic of both scientific speculation and philosophical debate. The idea of traveling forward or backward in time has fascinated thinkers for centuries, but relativity has provided a theoretical framework in which time travel becomes a plausible possibility, at least under certain conditions. According to the theory, as an object approaches the speed of light, time for that object slows down relative to a stationary observer. This opens the door to the possibility of traveling into the future, as someone moving close to the speed of light would experience time much more slowly than someone who remains stationary. This form of time dilation has been confirmed experimentally with high-speed particles, but it also raises fascinating questions about the nature of time and the possibility of traveling through time. Furthermore, general relativity predicts the existence of closed time-like curves, which are paths in space-time that loop back on themselves. These paths, theoretically, could allow an object or person to return to an earlier point in time. However, the concept of closed time-like curves raises numerous paradoxes, such as the famous grandfather paradox. If you were to travel back in time and prevent your grandfather from meeting your grandmother, would you cease to exist? These paradoxes challenge our understanding of the nature of time and causality and raise difficult questions about the possibility of traveling through time without violating the fundamental principles of causation. Relativity also has profound implications for our understanding of the universe as a whole. In the context of cosmology, the theory has given us new insights into the nature of space, time, and the evolution of the universe. General relativity predicts that the universe began as a singularity, a point of infinite density and temperature. This singularity is thought to be the origin of the Big Bang, the event that marked the beginning of the universe. The theory suggests that space and time themselves were created in the Big Bang, leading to the idea that the universe had a definite beginning. This raises philosophical questions about the nature of creation and the possibility of a first cause that set the universe into motion. Was the Big Bang truly the beginning of everything, or is the universe part of an eternal cycle of creation and destruction? Finally, the theory of relativity also challenges our concept of the observable universe. According to general relativity, the fabric of space-time is not static, it is constantly expanding. As the universe expands, the distance between objects in space grows, and this expansion causes distant galaxies to move away from us. In fact, the most distant galaxies are receding from us faster than the speed of light, which means that their light will never reach us. This creates a boundary to the observable universe, beyond which we cannot see. This raises fundamental questions about the nature of knowledge and observation. Einstein's theory of relativity, both special and general, has undergone extensive testing and validation over the years, earning its place as one of the most important and well-supported theories in the history of physics. The accuracy of its predictions has been confirmed through numerous experiments, astronomical observations, and technological applications, making it not only a theoretical achievement, but also a practical cornerstone of modern science and engineering. The experimental validation of relativity has been essential in ensuring its status as a universally accepted theory, and its successful predictions have allowed scientists to expand their understanding of the universe in ways that were once unimaginable. The first major test of special relativity came in 1908, just a few years after Einstein published his theory. The phenomenon of time dilation, a key aspect of special relativity, was observed experimentally in the behavior of fast-moving particles. Physicists discovered that particles like muons, which are unstable and decay rapidly, would survive longer when traveling at high speeds than when they were at rest. This observation supported the idea that time slows down for objects in motion, as predicted by Einstein. Later, the accuracy of this prediction was confirmed through numerous other experiments involving fast-moving particles, particularly those observed in particle accelerators. One of the most famous experimental tests of special relativity took place in 1971 when Joseph Haffel and Richard Keating performed a groundbreaking experiment involving atomic clocks. They flew 2 atomic clocks on commercial airliners around the world, one traveling eastward and the other westward. Upon their return, they compared the clocks with a reference clock that had remained stationary on the ground. According to Einstein's theory, the moving clocks should show different times because of the effects of both time dilation, due to the velocity of the planes, and gravitational time dilation, due to the altitude at which the planes were flying. The results were striking. Both moving clocks showed time shifts that perfectly matched the predictions of special and general relativity. This experiment demonstrated that the effects of time dilation were real and measurable, providing direct evidence that Einstein's theory held true in practice. In addition to the experimental verification of special relativity, general relativity has also undergone rigorous testing and has consistently passed every challenge thrown at it. One of the earliest confirmations of general relativity came in 1919 when British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During the eclipse, Eddington measured the deflection of light from distant stars as it passed near the sun. According to general relativity, light traveling through the curved spacetime around a massive object like the sun would bend, causing the stars' positions to appear slightly altered. Eddington's measurements confirmed that the deflection of light was exactly as Einstein had predicted, providing one of the first major pieces of evidence for the theory of general relativity. This observation catapulted Einstein to worldwide fame and cemented general relativity as a powerful and accurate description of gravity. Another key confirmation of general relativity came in the 1960s with the discovery of the phenomenon known as gravitational redshift. Gravitational redshift occurs when light moves away from a massive object, such as a planet or a star, and is stretched to longer wavelengths due to the warping of spacetime. This effect was predicted by Einstein and was confirmed through experiments measuring the light emitted from stars and other astronomical objects. The redshift of light observed from these objects matched the predictions of general relativity, further validating the theory's accuracy. Perhaps one of the most extraordinary tests of general relativity came in 2015 with the first detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as 2 black holes colliding. These waves were predicted by Einstein's general theory of relativity over a century ago, but until 2015, they had never been observed. When LIGO detected the faint vibrations caused by gravitational waves from a black hole merger, it confirmed a long-standing prediction of general relativity and opened up a new era in the study of astrophysics. This discovery not only verified a crucial aspect of Einstein's theory, but also demonstrated the ongoing relevance and power of relativity in understanding the most extreme phenomena in the universe. The theory of relativity has also been tested in the context of high-energy particle physics. In particle accelerators, where particles are accelerated to speeds close to the speed of light, relativistic effects such as time dilation and mass increase must be carefully accounted for in order to predict the behavior of particles. These effects are routinely observed and measured in particle colliders like the Large Hadron Collider, LHC, where particles are accelerated to near-light speeds. The success of these experiments and the agreement between experimental results and relativistic predictions serves as further evidence that Einstein's theories accurately describe the behavior of matter and energy at both macroscopic and microscopic scales. In the realm of modern technology, the theory of relativity has been tested and confirmed through its applications in everyday systems. One of the most notable examples is the Global Positioning System, GPS, which relies on a network of satellites orbiting the Earth. GPS satellites travel at high velocities and experience weaker gravitational fields than objects on the surface of the Earth, both of which affect the passage of time. To ensure that GPS systems provide accurate location data, engineers must account for both special and general relativistic time dilation effects. Without these corrections, GPS systems would quickly become inaccurate. The fact that GPS systems work flawlessly in our daily lives provides compelling evidence that Einstein's theories are accurate in practical, real-world applications. Additionally, the advent of modern astronomy and space exploration has provided numerous opportunities to test general relativity in new and exciting ways. Observations of the behavior of objects near massive bodies, such as black holes, neutron stars, and white dwarfs, offer direct evidence of the curvature of space-time predicted by general relativity. The detection of black holes and the observation of their interaction with nearby matter, including the bending of light around them, further confirm the accuracy of Einstein's predictions. The recent image of a black hole captured by the Event Horizon Telescope in 2019 was another triumph for the theory, showing a massive black hole at the center of the M87 galaxy and providing a visual confirmation of general relativity's predictions regarding the event horizon and the behavior of light around such an object. Relativity has even been put to the test in the realm of cosmology, where it has been used to model the behavior of the universe as a whole. The theory's predictions about the expansion of the universe, the behavior of galaxies. In conclusion, Einstein's theory of relativity has not only revolutionized our understanding of space, time, and gravity, but has also reshaped the very way we view the universe. Its groundbreaking principles have withstood the tests of time, both in the laboratory and through the lens of modern technology, and continue to guide scientific progress. The legacy of relativity extends far beyond its initial impact on theoretical physics. It has laid the foundation for countless innovations and deepened our understanding of the cosmos. As we continue to explore the mysteries of the universe, Einstein's theory remains a vital tool, helping us unlock the secrets of space, time, and everything in between. Relativity reminds us that the universe is far more complex and interconnected than we could ever have imagined, and it invites us to keep questioning, exploring, and discovering. Thank you.